Hello everyone, welcome back. So far we have looked at several things in this course, including unsupervised learning, supervised learning, and in unsupervised learning we looked at the k-means algorithm for clustering, and in supervised learning we looked at the k-nearest neighbors algorithm, the decision tree algorithm, and at a high level the neural network algorithm as well. So in all these algorithms that we have seen so far, one thing was common. The data was given to us and then we were asked to do something. In the unsupervised learning problem, we were given, let's say, 1000 data points, and then we were asked to cluster them into a group of data points. In the supervised learning problem, we were given, let's say, 1000 data points along with some labels, and we were asked to build a model that, given a new point, will predict whether the class is 0 or 1. The common thing is that data was given to us as a batch, right? So we were given 1000 data points. That 1000 is what I mean by when I say we are given a batch of data. But in a lot of real world situations, you may not have a batch of data given to you. The data might arrive one at a time. Now, here is a point where you can pause and think, where are some applications where do you think the data cannot arrive in a batch, but then it will arrive one at a time? While you think about that, let me tell you what the name of such problems where data arrives one at a time is generally called, right? So these problems are called as sequential decision making problems. So the sequential word means that you are not given data in a batch, whereas you are given data one at a time in a sequence, and what you have to do is you have to make decisions in a sequence. So what we are going to do or study in this module is different types of sequential decision making problems, and I will give you some examples for these problems, and then we will look at one problem and we will try to solve that in a special case. Okay. So what we are going to do now is look at three different type of problems which are all sequential decision making problems. And so these are some problems that we want to look at. And then we will discuss what are some commonalities about these problems and what are some differences about these problems, right? So and we will then pick up one of these problems and try to solve that problem. Okay, so that's the goal of this module. Okay, so here is the first problem. So this problem is what I am going to call as stock market prediction. So what is the stock market? A stock market is one where you have a bunch of stocks. Stocks are basically companies listed under some exchange, and now what you can do is you can invest your money in the stock market. And now if the company performs well, then the money goes up. If the company does not perform well, then the money that you invested goes down, right? So let's say we have a company named M, right? So that's just some company M. Now I have some stocks of this company. Let's say I have one stock of this company. What does that mean is that I own a very small piece of this company. That's what saying that the statement that I have a stock of this company means, right? So I'm a owner of a very small part of this company. Now now I can decide whether I want to buy one more stock of this company and become a slightly larger owner, or I want to not buy anything of this company, right? So that's a decision I can make. Now the way it works is as follows. We have this company's M whose stock I want to decide to invest or not invest every single day, right? Every morning I wake up and now I have to make a decision whether I am going to invest in this company or not invest in this company. Now that is the decision that I make in the morning. By evening, right, so what happens is that the company's stock value either goes up or goes down. Now let's say I invested in the company in the morning and the stock value went up in the evening. That means that I have made a profit. Now let's say I invested in the morning and the stock market went down in the evening. That means that I have made a loss, which I don't want to happen. Let's say I did not invest in the morning and the stock market went down, then I did a good thing, because I did not invest but the stock market went down. Had I invested, I would have ended up in a loss. So if I did not invest and the stock market goes down, I prevented myself from suffering a loss, so that's a good thing. Whereas if I did not invest but the stock market went up, then that's a bad thing for me, because I lost an opportunity to make money. Had I invested, I would have made money at the end of the day. I would have made some gains, but I did not invest, and so that's a bad thing for me. Now I don't know what's really going to happen at the end of the day, because I need to make the decision at the beginning of the day, right? So on the morning 9 o'clock, I need to make a decision whether to invest or not, and evening 5 p.m. I will know whether that decision was a good decision or not. Now let's say I don't know anything about stock market to make meaningful decisions. So what I'm going to do is, I'm going to rely on a set of experts. Let's say these experts are some of your friends who have some knowledge about the stock market, right? So these experts are going to give you their advice, right? So what does that mean? Every day morning I get up 9 a.m. I need to make a decision whether to invest or not. Before I make the decision, I ask my friends or the experts, hey experts, tell me, what do you think I should do? Now let's say you have 100 friends or 100 experts that you are asking this question to, and these experts are going to give you an yes or no answer, each of them, right? So they are going to tell you whether it's a good idea to invest or not invest. Okay, and now you have heard from all these experts. It's not necessary that all of them are going to say yes or all of them are going to say no. Some of them might say yes, some of them might say no. Whatever it is, you hear their expert advice, and now you as an individual makes a decision, you make a decision whether to invest or not. Now the decision that you make will obviously somehow depend on the experts. How exactly it will depend, etc., we will talk about later, but somehow you are getting the information from the experts, and then based on that you are making a decision. Now you are going to be judged for the decision that you made, because if you decide to invest and if the stock market goes down, then that's a bad decision, and there are other possibilities that we already spoke about. Now this is the setup. Now the goal is to make good decisions. Now why is this a sequential problem? Because every morning this scenario repeats. The next day morning you again get up, and then these experts are again going to give you advice, and then you are going to look at the advice and then make a decision, and the stock market might react differently today. It's not necessarily that daily the stock market will either go up or go down. That's not under your control, right? So that depends on so many other things. How did the company perform? How did the company's competitors perform? And so many other things, right? So let's not worry about that, right? So you don't have control over whether it's going to go up or down. You only have control over what the experts are saying. Well, you have that information, and then you want to make a decision, and at the end of the day you are revealed whether the decision was good or bad, and over time your goal is to make more and more good decisions, right? So this is problem number 1, which I am going to call as stock market prediction problem. Okay, so at this point I don't want you to think about how to solve this problem, right? So we'll come to that later, right? So what I am trying to do now is to give you a set of problems, and then we will discuss what are the commonalities of these problems, are there any differences between these problems, and then we will ask ourselves, once we know the subtleties of these problems, then we will ask ourselves how to solve this problem, and that's when we will get into the algorithmic aspects of it, right. So, how can I create an algorithm that will solve this problem, etc., that will come later. Now, problem number 2, this is problem number 1 that we have already seen. Now, I am going to tell you problem number 2, which is healthcare. I am going to call it healthcare expert advice. Okay. In this problem, you are going to imagine yourself as a doctor, right? And now you have patients coming into your office, to your hospital, let's say, and then these patients all have similar set of symptoms, let's say. Now, you have to prescribe a medication to this patient, to these patients who come in, right. So, daily, let's say one patient comes in, and then you have to say, which medicine should I give to these patients. Now, let's say there are 4 different medicines, okay, for the same set of symptoms. Now, you do not know which medicine will work the best. Now, you can choose to, let us say we will call that tablet 1, tablet 2, tablet 3, tablet 4, right. So, you have 4 different tablets for the same set of symptoms, and all of these, let us say, are new tablets that have come in the market, and you as a doctor are not sure which of these is the best suited for the patients. Now, what happens is you have to prescribe one of these, and now let us say you prescribe a medication to the patient. Now, the patient goes back home, takes the tablet, and in the evening the patient reports saying whether that patient is better or worse. To make matters simple, let us assume that the morning 9 a.m. every day one patient walks in with a set of symptoms, and now you have to decide which tablet to give to the patient. You make a decision, and the patient goes away to home, takes the tablet. Evening 5 p.m. the patient reports back to you saying whether the patient is feeling better or not better. Now, if the patient says he or she is feeling better, then you know that that tablet seems to be working for this patient. Now, tomorrow another patient might come, let us say you prescribe the same tablet. At the end of the day, that patient might say this tablet is not working for me, right. So, I am actually feeling worse, or my fever has not subsided, or something like that, which means that the same tablet might work for one patient, might not work for another patient. That can happen, right. Now, which means that the next day third patient comes and you will want to try a new tablet and so on, right. So, again we are not getting into the algorithmic details. How am I going to prescribe these tablets? That is not what I am talking about at this point, but what I am trying to say is what is the setup. The setup is every morning a patient walks in, you make a choice among one of these tablets, and then the patient reports back saying whether the tablet worked or not worked for him or her. And over time you want to learn to make the right choice, right. So, if a tablet works for 90% of the people, whereas another tablet works only for 20% of the people, you want to find which is that tablet that works for most of the people and then prescribe that tablet more often. In fact, you want to make sure that you are prescribing the right tablet as a doctor, so that the patient's health improves over time, right. So, now this is what I am going to call as the healthcare problem. Let me just call it healthcare problem, and again this is a sequential problem, and you can see already why it is, because every day a new patient walks in and you have to make the same choice, right. So, which of these tablets to prescribe to these patients. This is problem number 2. Now, the third problem that I want you to consider is the following problem. This is what I am going to call as a robot navigation problem. So, in this problem what you have is a grid. Let us say think of this as your as the floor of your house, and now there are a lot of objects kept of different shapes and sizes that are kept in the floor. Now, you have a robot, right. So, we have a robot, which I am going to put it like this, Now for simplicity, let's say there are a lot of grids in the house. You can divide the floor into grids, and the robot is, this is where the robot starts, and then you want the robot to reach here, right? So this is the goal. The robot starts at a certain place and has no idea about the objects, where they are placed or anything, right? So the robot is a physical object, and now it needs to reach the goal, right? So the moment it reaches the goal, it knows, let's say, that it has reached the goal. Now what can the robot possibly do? Well, the robot has certain actions that it can take. For example, it can move one step forward, or it can move one step left, it can move one step right, or it can move one step back. Now not all these actions are possible in all grids. For example, in the start grid, what are the actions possible? Well, the only two actions that are possible are, it can either move forward or it can move to the left from my point of view, right? So it cannot move below because there is no below, right? So it is at the bottom, and it cannot move further to the right because it is at the bottom right. But in other places, for example, if the robot was here, now it can move in all four directions. Now what is the nature of the problem? Well, the robot makes a decision to either move forward, backward, left or right, and now after it makes a decision, it gets a feedback saying whether the decision is good or bad. And what kind of a feedback it gets? Well, if the robot is at this point and then it tries to move forward, it's going to bang into this object, and now it cannot move forward, right? So it has to stay there. So that's the feedback that it gets, that moving forward is a bad idea, because you will go and hit an object that is placed there, because a priori the robot doesn't know where the objects are, right? So before the game starts, the robot doesn't know where the objects are or anything about the layout of the room, etc., etc. It has to figure that out over time, right? So now you can think of the robot's decisions as a set of sequential decisions that it is making, right? So there is a time component here. So every time instant, the robot is making a decision, and that decision will and then it gets a feedback whether the decision is good or bad. And now based on that feedback, hopefully it will learn to navigate through this complicated grid and then finally reach the goal state, right? So this is problem number 3, right? Now let's try to think of these 3 problems and ask ourselves, what are the things that are common across these 3 problems? Now it's a good time to pause and think what you feel are things that are common across these 3 problems. Now let me tell you what might be common across these 3 problems. In fact, what are common across these 3 problems? The first thing that is common, right? So common properties. When I say properties, properties of the setting that we have seen across stock market prediction, healthcare and robot navigation. One of the common properties, and this is the most important property, is that sequential decisions, right? So, and this is what makes these kind of problems different from the supervised learning or unsupervised learning problems that we have seen so far, because your data is not given a priori. When I say a priori, it means that data is not given earlier as a batch, but then you are collecting data as you play the game, as as the decisions are made. So the decisions are made in a sequential fashion. So that is the first point. The second point is that in a supervised learning problem, standard supervised learning problem, you are given the data, which means that you are given the features and the labels corresponding to that feature also. Now here, let's think of the stock market prediction problem, for example. Every day in the morning, I wake up and then I get a data point. I can think of it as a data point. What am I thinking of as a data point? The expert advice, right? So the 100 experts who are giving me their advice, I can think of that as a data point, right? So it's a 100-dimensional data point where some experts are saying 0, some experts are saying 1, right? So I can think of it as a 100 numbers, right? So some of these are 0, some of these are 1s. Now that's the data that I'm given, and based on that data, I have to make a decision. I have to predict the label whether I should invest or not. In a supervised learning problem, you would be given both the features and the labels, and you want to learn a mapping from the features to the labels. Whereas in this problem, now just the features are given, which is all the experts advise, and now I have to make a decision whether I want to invest in the stock market or not, and after I make the decision, the label is given to me, right? So the label is the feedback that I get. Similarly, in the healthcare problem, the patient walks in, and now I make the decision, and after I make the decision, the feedback, I get the feedback whether that decision was a good decision or not. Same with the robot. The robot makes a decision, and then the robot gets a feedback whether the decision is good or not, right? So the feedback is another common property of all these problems, right? So the decision is made, and then the feedback comes post the decision making. Now, then let me ask you all a very, very important and fundamental question. Are these three problems the same problem, right? So, are we trying to solve the same problem? In other words, for example, in a supervised learning setup, it doesn't matter whether you are trying to predict whether, given a customer profile, whether I'm going to say this customer will pay the loan back or not. That's one problem. Whereas another problem could be, given an email, I want to say whether this email is a spam email or not spam email. Of course, the data is going to be different, the labels are going to be different. In one case, it will be the customer history, and the label is whether the customer paid the loan back or not. In the other, it is going to be an email, and the label is going to be whether that email is spam or not. That difference will be there, but then as a problem, you have some features, you have some labels, and then you want to learn a mapping from features to labels, and that's what we are calling as a supervised learning problem. Both loan history, customer loan payback prediction, and email spam or not spam classification are both supervised learning problems. Similarly, I am asking, are these three problems the same problem, or are there any basic differences or fundamental differences among these three problems? I know it's a very open question, but then it would be interesting if you can pause and think about that, if you are trying to see any subtle differences between these problems.